Anyways, yeah, so thanks everybody for coming. So I'm going to talk a little bit about scoop probes, or single point sample entry return probes. I'll do this without a slide now, that's okay. So the issue that we're going to try to address, and there we go, we're going to talk about what's the scoop. The issue we're going to try to address with this is the fact that most extractive analyzers, most grab sampling stations, we'd like to have a fast loop there if we could. When we're looking at analytical measurements, we'd often like to get the sample there as quickly as possible, and especially if the analyzer or the grab sampling panel is a distance away from where we're going to do the measurement, we'd like to get high velocity flow rates over there. And so, you know, if we look at this, let me just see if my pen's working here. No, it's not. Okay. If you look at that figure in the bottom, you can see we have, you know, if we have a direction of flow, we have some differential pressure, and we've got a high pressure point and a low pressure point, it's pretty easy for us to get continuous flow through this loop. So I got this thing positioned, okay? But it's going to require some differential pressure. And that usually means that we're either going to have process differential pressure available, or we're going to have to put something like a sample pump in, or we're going to put in a low pressure vent. We're going to vent to a flare header or maybe atmosphere. We'd like to find a way to be able to create fast loops without having to meet all those requirements. So, like we said, many analyzers, many samplers don't require a lot of flow for them to operate, but we need flow in the fast loop in order to get a good response time. If you've been through the Tony Waters training or came to my class this week, you know, we talk about how the time delay in a system is the volume divided by the flow rate. So if we want to get fast response, we either have to keep our sample system volumes low, or we have to have a lot of flow. Fast loops will help to ensure that we get a fresh sample over to where we're going to do our measurement, and they often have to be engineered properly. If it's liquids, we often have to worry about pressure drops. If it's gases, we have to worry about compressibility. And so there's a lot of factors that can come into play when we're trying to figure out, well, how are we going to put a fast loop, or how are we going to design a fast loop for, say, a sampler. And there's a lot of issues and common problems that come up when we start to consider, how am I going to implement a fast loop at my facility? One of the common ones that we'll see is we only have one sample point. So we have a sample point to measure from, but we don't have a low pressure return point. So we have to try to figure out, where is that low pressure return going to go to? If we don't have a low pressure process point, now we've got to go, well, I can't return back to the same pressure, so maybe I'm going to need a pump. If we're going to return to a low pressure place like the flare header, we may be concerned about the volumes that we're going to put there. So one of the solutions which might come up fairly often is that we are going to, let me just see if I can pick up a pen here. There we go. Let's see, does that work? One of the solutions which might come up fairly often is people will say, well, we'll just put in a pump. Sounds like a great idea. We'll just put in a pump. It's easy, right? Well, as soon as we put in a pump, we have a whole bunch of issues that can potentially arise with that. First of all, process pumps are going to be expensive. So we're going to have costs associated with the pump. We're going to probably have a lot more maintenance because pumps require maintenance. I frequently, when we're looking at analyzer installations, I say, I don't like to put pumps in because I make my analyzer mechanics become pump mechanics. They're fixing the pumps all the time. There's going to be a sizing issue. We had a meeting this week talking to some people, and they said, well, the problem was they oversized the pump, and it was cavitating on the inlet side. And so who's going to do the sizing for the pump? Did it get sized properly for my application? And then we also say, well, you know, it becomes this little bit of an engineering avalanche. We're going to put in a pump. Well, where are we going to put the pump? Well, we're going to pour a pad for it. Is there electricity where we're going to put the pump? No, we're going to actually do some civil. We're going to run electricity over there. Well, how are we going to know if the pump's overheating? Oh, we're going to put a temperature sensor in, and then we're going to bring that data back to see if the pump's overheating. What are we going to do if the pump fails? Oh, we'll do it twice. We'll put redundant ones in. And so we get into this little avalanche of costs and complexities in our analyzer installations. Um, but wait, there's more. If we're running gas analyzers will often run at low pressures. You know, if we look at something like our gas chromatographs or an online spectrometer, UV vis spectrometer, they'll often be running near ambient pressures. And if our sample gas is at high pressures, if it's, say, a natural gas pipeline, I can't return process fluid back to the high pressure spot very easily. You know, it's tough pumping the gas back up to, say, 60 bar if I'm sampling from a high pressure natural gas pipeline. So it can be difficult to return to process. If I vent it to atmosphere, which a lot of fast loops will sometimes, these things are, if they're venting to atmosphere and I'm running natural gas, well, now I've got significant methane emissions. And of course, in these days, greenhouse gases, methane being anywhere from 25 to 40 times the greenhouse gas equivalent of CO2, if I've got a 5 liter a minute bypass venting to atmosphere, it's a significant amount of GHG emissions. If I'm taking it to my flare line, I've put an extra capacity into my flare. You know, if I've got a whole bunch of analyzers in the plant and they're all venting to the flare header, well, now all of a sudden my environmental guy goes, hey, can you guys put less stuff to my flare? And then yet another problem in a place where we often don't put a fast loop in, but we really need one, is near vaporizers. If we're putting a liquid vaporizer in near the sample tap, we would really like to have a fast loop in front of it, because vaporizers take very, very low liquid flow rates. So if you look at a vaporizer that's running about 1 liter a minute of gas on the gas phase side, it might only be vaporizing 2 or 3 milliliters a minute of liquids. And again, since time is volume divided by flow rate, what happens if we have very low flow rates on the inlet to the vaporizer, we can have very long time delays. Usually, if we have time delays in a liquid system that's using a vaporizer, the time delay is happening on this side of the system. And the problem is, if we're putting vaporizers out near the sample tap, while we're near a process pipe where everything is one pressure, we have no low pressure return. And so these are going to run very, very slow on the inlet side. I think I do the calculations on a slide coming up, or I talk about the calculations on a slide coming up. But if that vapor is sitting on a 2-inch pipe nozzle that doesn't have a probe in it, you'll have about an hour or an hour and a half of time delay just to try to clear the pipe nozzle. Put a probe in, you might get it down to 20 minutes. But we're going to talk about a way to be able to do this a lot faster. So the way we're going to approach this is by going back, you know, I'm a physicist by trade. I go back right to the fundamentals of physics. Okay, let's talk about Bernoulli's principle. Bernoulli's principle tells us that when we have fluid flowing down a pipe, wherever the speed slows down, the pressure increases. And whenever the speed increases, the pressure drops. And this all comes out of kind of Bernoulli's equation. What this ends up meaning is that if we flow towards a cylindrical object like my pen, where the fluid hits the front surface of it, the pressure is higher. As the fluid shears around the object, all the fluid that normally would have liked to stay flowing in a straight line has to go around that object now. So it actually accelerates as it goes around the sides. And what we end up with is low pressure spots on either side of this. This principle has been applied by a bunch of people. There's ExxonMobil patents that have talked about this sort of an idea. Shell has looked at this for LNG vaporization in a system that's sort of like the one I kind of show at the bottom here. And you know, there's commonly been put in systems like this where if the direction of flow is coming in, they cut a probe angled towards the direction of flow. Now the flow impacts on that, drives its way up through that piece of tubing, runs across. They have another probe cut at the opposite angle away from the direction of flow. It creates a low pressure zone, and now you can get continuous flow through that loop and vaporize that flow. Gives you faster response at the vaporizer. However, it may not be the best use of the energy and the capacity of that pipe to actually generate differential pressure and flow. So we're going to talk a bit about how we can optimize a system like this. So again, if I am flowing around a cylinder, if my direction of flow is going this way, oops, I just triggered my video before I wanted to. Oh well, we'll watch the video then. So the bottom video is a mathematical simulation of flow in a pipe. And you can see what happens is as the flow increases, the red zones are where there's building up low pressures on the side. There's a little blue spot right at the front, in front of that probe, which is actually a low pressure zone. And then you see the Kalman vortices forming. This is the things that cause flow, probe resonance. And then they slow the flow back down again. It's kind of a cool little video. YouTube has all sorts of great ones for flow around cylinders. The important things to get from is if you solve the Navier-Stokes equation, if you do computational fluid dynamics, what you find is the high pressure region is out in the front of the probe, and the lowest pressure regions are on either side of the probe or that cylindrical object that's in the pipe. So how do we want to use that? Well, we kind of know flow likes to go from high pressure zones to low pressure zones. So if we could find a way to create flow between the front of that pipe and the sides of that pipe, we could use it to drive flow through a loop. So we'll talk a bit about how we do that. So I'm going to be using kind of this reddish colors to indicate where the higher pressures are, and blue to indicate where the lower pressures are. So what we start out with is a probe, and it has a mechanical insert in it, and part of that mechanical insert is a thing which we refer to as the scoop. And we call it a scoop because it looks an awful lot like a scoop. It looks like it'd be something I'd use to scoop dirt up. The unique thing here is there is a very optimal curvature to introduce in here, because what we want to happen at that scoop is we want fluid that's flowing along that's horizontal to flow around it and change direction by 90 degrees. So when people just cut it off at an angle and let it impact on an object, some of the pressure, the available delta P, the available energy that we could use for driving flow is being lost in the turn. So we did a whole bunch of computational fluid dynamics to try to say, how do we optimize what happens within this region? And I kind of drew that a lot more crudely here. This is what happens when my mechanical engineer does it. This is what happens when a nerd like me sits down with PowerPoint and says, I need to make something that kind of looks like that. But you get the idea. We're going to go around that corner. So what happens is if flow is coming in towards this, we build up a high pressure zone right in front of there. That is going to push fluid into there and have it turn around that 90-degree turn and start wanting to flow up. We attach a central tube onto there, and that way we can take our sample and allow it to flow up that central tube. At the same time as fluid is flowing and impacting on this probe, there's low pressure regions on the side. So we said over here on the sides of the tube, there's going to be a low pressure region. So we make a big set of ports on either side of the probe body, and those become our return points. Fluid that's gone up through the center region, let me just pick a different color here. Fluid that's gone up through the center region returns back through this annular region and goes out those ports and returns back into the process lines. So we put large ports on the sides, lots of surface area, and there's a place for the fluid to escape back into the process. And so by optimizing that inlet scoop and those positioning and shape of those side ports, we can basically increase by about a factor of 2 how effectively we can use the differential pressure that's available to drive flow through that fast loop we talked about. So by fast loop, what I mean is it ends up looking kind of like this. We have that probe sitting there. It's driving flow out the central region, returning back flow into the annulus. And what we do is make that into a loop. Run some tubing around it. You preferentially use fairly large bores so they don't have much pressure drop. So this creates a fast loop that allows us to extract from the process pipe and return back into the process pipe while at the same pressure. There's effectively no difference in pressure. There's a few kPa, but it's enough to continuously drive a loop through there. One port of entry. We can even include a little bit of sample conditioning in there. We can put a bypass line of a filter there. Or we can put an inline sensor in there, like a Raman probe, or an NIR cell, or an oxygen probe, or a pH probe. So if you've got a water application, you say, I'd like to have a pH probe that I can actually maintain. I could put a probe like this in, put isolation valves on either side of the return side, nice big bore ball valves or gate valves. Again, I don't want flow restrictions. And then I just have it flow over my pH probe. The limitations that we have to consider with this is physics is going to determine how much differential we can actually create. Hopefully this animation is going to go. Let's see. There you go. So there's actually a computational fluid dynamics simulation of this probe in operation. Fluid flowing along the pipeline. So you can see the vortices that kind of show up around on the back side, but it drives flow up the center side, returns stuff back on the return side, and back into the process pipe. So how do we apply this? What's good about it? In gas phase applications, they work really, really well. We have no issues with priming because gases are compressible. And so for gas phase applications, we can put this into any line that has a high velocity gas flow. It's going to drive flow up through the center region. We might use that to drive past a filter. But again, it could be driving through something like a flow cell for a Raman analyzer. Could be driving through the flow cell for a near infrared or an infrared analyzer. It could be a hydrocarbon dew point analyzer sitting there. We can use it to drive continuous flow. And all of the flow gets returned to the process, even if it's at high pressure. So if we have a stream that has, say, H2S in it or methane we don't want to release, it lets us return back at pressure. In a typical example, if I've got about 10 meters per second of flow, which is a typical natural gas pipeline, if I got 10 meters per second of velocity of my pipeline, I will end up, and I put in 150 feet of 3/8 inch tubing to run my fast loop over, and I'm at 45 bar in that pipeline, typical natural gas pipeline, 600, 650 pounds. I'll drive through that loop at about a meter a second. So I get 30-second response time. This goes completely against everything I've ever taught all of you in a sample conditioning class, where I've said, if you've got a high pressure gas, the first thing you want to do is put a regulator in to lower the pressure. We're actually saying we're going to build this fast loop at high pressure. It goes completely against everything we talk about in our sample conditioning classes, where we say if you want fast response time, go with really narrow diameter tubing. This loop will run faster if I put larger diameter tubing in, because the tubing contributes less pressure drop then. But it allows me to create a fast loop that will continuously run and return to process. Liquids applications become more challenging. They're challenging because we don't generate a lot of differential pressure with these. Liquid velocities in pipelines are usually fairly slow, 2-3 meters a second. At 2 meters a second of process flow, if we have something that has around the density of water, we'll only generate 400 millimeters of water differential pressure. It's equivalent to 400 millimeters a head. This is about a pound. We can't get over a lot of hydrostatic head. If you talk to people who put scoop probes in or flow impact probes on liquids applications, they'll say, we tried it and it didn't work. And it doesn't work if you don't install it properly. If you put that probe in vertically on the top of the pipe, the differential pressure has to overcome the hydrostatic head. If the line runs up towards the analyzer, it will never prime. To do these installations, we have to try to make sure that the probe is installed on the side of the pipe, and ideally the analyzer is lower than it, So we have a downhill run for liquids that will self-prime. Otherwise, we've got to put a mechanism for priming in. So when we do the installations for liquids, our ideal installation is to sample off the side of the pipe and ideally have the analyzer be lower down, so that, or the composite sampler, the grab sampler, whatever it is. Otherwise, we're gonna have to consider how are we gonna get that thing to prime. Once it starts to flow, it's a siphon and it just keeps on going. But we may have to add a mechanism for priming if we're gonna try to run uphill. So one of the great applications for this is things like vaporizers. We see a lot of vaporizing regulators get installed in the petrochemical facility, and you'll go into a plant, you'll be walking along, and there's a vaporizer, and it's somewhere up there in the pipe rack. And you go, how do you guys maintain that? Oh, we don't. We never go up there. How do you know it's hot? We don't. We run steam to it. How's your steam traps? I don't know. I haven't checked. Steam is one of two temperatures. It is really, really, really hot, or it's cold. Depends on how your steam traps are. And so, so when we have vaporizers up there, and if they're coming right off of a pipe nozzle like this, they can have a lot of time delay before we get into the vaporizer. And they can have really slow response times. So like I said, went through the calculations. On a 2-inch pipe nozzle without a probe, you probably have an hour of time delay getting into the vaporizer. If you add a probe that's about 1 foot long of 1/2-inch Sched 80 pipe, you might be down to 15 minutes. Big time delays up there. These vaporizers only run at a few milliliters a minute. We can put in something like a scoop probe, horizontal on that same upper pipe run. Run 2 pieces of 1/2-inch tubing down. Put that vaporizer down at grade now. Put that vaporizer someplace where there's a platform where a guy can stand on it and actually do maintenance on it. And all of a sudden, we can get that fast loop going. It's gonna be running somewhere between 1/2 meter a second or so. If I got 10 meters of lines, that might be only 5 minutes or 5 seconds to get down to where that vaporizer is. Now I have a fast loop in front of the vaporizer, continually have fresh sample there, and I end up taking that 15 minutes or hour response time down into the 30 seconds or a minute kind of range. Similarly, it doesn't have to be a vaporizer down here. Again, it could be a Raman analyzer cell, an infrared analyzer cell. I could have taken my flow cell for an infrared analyzer, run fiber optics over to it, and done an analysis that way. So here's one actually, it's not my favorite installation, because these guys put it right in on the elbow of a pipe, but this is an NGL pipeline, and they put the probe into the side of the pipe. They're running a fast loop out. The fast loop is running over here, running over to a JP3 infrared analyzer, comes straight out of the JP3 infrared analyzer, goes right back into the pipe. So now they have continuous flow through that flow cell, and it's being driven just by the velocity in the pipeline. So I'm wrapping up here right away. Scoop probe applications and advantages. In the gas phase, they can return a fast loop directly to, and I should have probably put into a high pressure process. So we can mitigate environmental emissions and flare emissions. So we don't have as much environmental emissions, we have less flow going to the flare lines. We can use the same thing for grab sampling stations like composite samplers. So in natural gas and CO2 pipeline analyzers, we can make sure that all of our fast loops are returned to the process. We don't have an environmental, greenhouse gas emissions. For liquid fast loops, we've used these for grab samplers and for composite samplers. Fast loops to vaporizers is a great application because it gets around all that time delay on the front side. And then fast loops to any kind of inline analyzer. Raman, NIR, FTNIR, pH probes, inline oxygen probes, inline dew point analyzers. We were talking with the Kiko guys, they do a membrane extraction. Put that membrane extractor in a continuous fast loop. So that's it. That wraps me up. If there's any questions, I'd be happy to address them.
So normally we put the sample probes in with the bevel in reverse direction for filtering. What do particulates do to this, and have you looked at any type of loading?
Yep, yeah, so that's certainly potentially one of the issues. You know, I mean, if you've got a really, so the question is that, you know, normally we've always said, hey, you're gonna cut the angle of the flow of a pipe away from the direction of flow, at least in gas phase systems, because we're gonna pick up less particulate. And certainly that's true. We're gonna potentially pick up more particulate with this. Again, the nice thing is though, is we get to go with fairly large diameters through this whole thing. We typically run 1/2 inch, 3/4 inch tubing, so it's gonna be less likely to plug off that way. It could be problematic in a high particulate stream. Yeah. We have used it though on things like, we've done it on, used it on composite samplers for crude oil. So crude oil is usually, of course, got some sand, some water cut, asphaltenes, things like that in it. Any other question? Yes, sir.
Would you be able to use this as well, gas phase, in quite low pressures? I'm thinking of applications where you might have a toxic gas that you wouldn't want to have to handle once you've measured it. So a kind of a closed loop toxic, but at quite low sample pressures.
Yeah, it's really what drives flow through the system is, actually, let me put this two ways. So the answer is yes. So we've used it on flares, which are running atmospheric. You don't get as much differential pressure, but it doesn't take as much work, because the pressure you get is basically rho, the density of the fluid, times the velocity of the fluid squared. So as long as you've got velocity, you're going to drive flow through that loop. And you'll return into that same loop. So the answer is yes.